So now let's continue on to Module 5.2 and go through a sample problem solution. The problem we're going to look at now is a building example problem. So we can see here in our problem statement, they tell us we have a one-story building. It's idealized as 12-foot high frame with two hinged columns made from, they give us here our I-beam of W8 by 18, so we can look that up and figure out dimensions and more information from that. Has a rigid top and a natural period of 0.5 seconds. They want us to determine the maximum response due to a rectangular pulse of 4 kips with a duration of 0.2 seconds. They also want us to find the stress that's generated in the beams. So they tell us our section modulus is S is equal to 15.2 inches cubed. Our moment of inertia I is equal to 61.9 inches to the fourth. And our modular elasticity E is equal to 30,000 KSI. And we have our diagram up here. And we can see, okay, here's our height here of 12 feet. Here's the two I-beams right there, our W8 by 18. And here's a top rigid beam there. So shown here, we can reference back to some of our previous textbooks, go on the web, and we can find the dimensions based upon the fact that they told us we have an I-beam of W8 by 18. So within this, the I-beam, we have our top flange, we have what's called the depth on the side over here, and we have our web. So based upon the fact that we have a W8 by 18, we have a depth right here of 8.14, our flange is 5.25, and our web is 0.23, and it tells us it is 18 pounds per foot. So we can use this information, if necessary, to plug back into any of our equations as we're solving the problem. So I read out the problem statement as you read it in the book. We have a one-story building idealized as a 12-foot high frame with two hinged columns made from I-beams of W8 by 18 with rigid tops and a natural period of 0.5 seconds. So our natural period here is going to be our T sub n. They asked us to find two things. So in our setup, we write this out. We want the max response due to a rectangular pulse. We're doing the rectangular pulse of 4 kips. So we're going to call this P naught there with a duration of 0.2 seconds. Our T sub d. They also asked us to solve for a second thing here, our stress generated in the beams, our sigma right there. So this is our setup page. We can reference back to our problem statement, what they've asked us to solve for, and a couple of the variables that we're going to use for this, so Tn, Td, and our P naught. So for my setup page, as we typically write it, I want to clearly write out everything that's given to me. So between the wording of the problem, the diagrams, and the given information below our diagram, we have that our section modulus is given to us as S equals to 15.2 inches cubed. Our moment of inertia is equal to I of 61.9 and inches to the fourth. And our elastic modulus, E, is equal to 30,000 KSI. They also tell us our T sub d, our time duration, is 0.2 seconds. Our natural period, T sub n, 0.5 seconds. And our rectangular pulse, P naught, is equal to 4 kips. So now that I've had a chance to read through the problem statement, look at the given diagram, see all the information they gave us and what they're asking us to solve for, my next step before I start my solution is to think about key equations for what I'm looking for versus what I have. And it's not always very clear exactly which equation we should go for. So what I've chosen to do here is pick out a couple of equations. I think I may need to do some conversions between variables in order to solve for what they're asking us for. So I write that out here. I have sigma is equal to my moment divided by S, where S is my section modulus. I have my moment is equal to force divided by 2 times the height, because there's 2 beams there. And I have my column equation here, 3EI over my L cubed. So I have all of these here right on my setup page to reference back to as my key equations for if and when I may need to use these to solve for what they're asking us for in the problem statement. So now with all that information and the fact that we have our setup page ready to go and reference back to, we can begin our solution. So our solution page 1, first thing we want to do is to calculate the lateral stiffness. So that's where we can use this equation that we wrote in our key equations here, that our K of the column is equal to 3EI over our L cubed, where we can then plug in our known values. So we know we have our E given to us as 30,000, our I is given to us as 61.9, and our L, again, pay attention to, are we in feet or inches, so make sure we convert correctly. So we're given our L in feet, we want it in inches to match our other values, so we change our L over here to 12 times 12 inches per feet, and then we're going to want to cube all of that for our L cubed right there, and this gives us our K for our column there. So K for column is equal to, when we plug this in, 1.865 kips per inch. So K for 2 columns would be 3.73 kips per inch for our K value. So for the next step in our solution, we're going to take a look at our time ratio. We can go to page 110, section 5.2.1 of our textbook. We're looking at rectangular pulse loading. Now there we have this relationship here that TD needs to be less than TN over 2. Well, our TD is given to us in the problem statement as our 0.2. Our TN is given as 0.5. So if we take 0.5 divided by 2, that gives us a TD of 0.25 seconds, which is greater than the 0.2, so that's fine there. So go to our ratio TD over TN. Our given TD is 0.2 seconds. Our TN, again, was 0.5 seconds. So that ratio is 0.4 for our time ratio. Now with this value here, we can go down now to our R max equation. And this comes from equation 5.13 on page 120 of our textbook. So our R max is equal to 2 times the sine of pi times TD over TN. Or if we look at this here, rearrange it for our time ratio, 2 times the sine of TD over TN, our time ratio right there, times pi. So we can plug in, now we have this 0.4 for our TD over TN there. We can take that, plug it right back in for this guy right there. And we now have R max is equal to 2 times the sine times 0.4 times pi. So we do the math here, and our R max is 1.902. So the next part of our solution, we're going to solve for our displacement. We can do this by using the equation on page 132 of our textbook. We do that, we have that U max is equal to P over K times our R max value. We have our value here of 4 given to us in the problem. We have our K value here of 3.73. And we just solve for our R max to be 1.902. We plug those in, and our U max, or our max displacement, is equal to 2.04 inches. Next, we want to find our moment. So for our moment here, we have our F equivalent is equal to PO times our R max value there, so we can plug those in. F equivalent is equal to 4 times 1.902, or F equivalent is equal to 7.6 kips. So now, for our moment here, moment is equal to FEQ over 2 times our H value. We had that problem from the beginning. We can reference back. So plug in our known values. Now we have an FEQ. So we have moment is equal to that 7.61 divided by 2 times our H value. And again, we want to make sure this is in inches. We know it's 12 feet, and there's 12 inches in a foot. So our feet will cancel out there. We can plug this in, and our moment is equal to 547.8 kips. So for our normal stress, go back to our setup page, and we had our equation here. Sigma is equal to M over our S. Our S value was given to us in the problem statement. So sigma is equal to M, which is 547.8 from right up above here in kips, divided by 15.2 given to us in our problem statement. So our sigma is equal to 36.04 KSI.